Hello, this video is about the geographically weighted random forest using R when the data are uniformly spatially distributed. So when data are dense in one area and spread out in another, adaptive bandwidth is used. However, when we have a spatial distribution of the data, the fixed bandwidth has superior results. So the reason that it ensures that every local models cover the exact same geographic area, making the comparison between different local forests more consistent for physical interpretation. So when we search for the optimal bandwidth, we use fixed. So in R, the main library used is the Spatial ML, Spatial Machine Learning, and to install it. When I tried to R, it didn't work, so you have to go to the remote using this code, install the package through GitHub or through the DevTools. Okay. So let's go to R and start working. So you need to install 3 packages, the SF, TMAP, and the Spatial ML. So I already talked about how to install the Spatial ML. But yeah, here SF and the TMAP. You can get them from here, packages, and then install. And I type here. I already did. But for the Spatial ML, you need to go through the remote or the DevTools. So let's load the libraries. And the data set is found in this directory on my computer. I call the object my data. Okay. Okay, so let's load the data. Let's check, see the summary of the data set. Summary, my data. So it's the information. Let's look at the dimension. Then my data. I have 100 observation and 7 variables. That's all. For the sake of time, I reduce because it takes time to run to search for the bandwidth. And I have a lot of data. So with the 100 observation I took, we'll see how much it will take, how much time it's going to take. So let's define the coordinates. We need the coordinates to work, so defining the coordinates. It's called chords equal to my data, and we take from my data, we take x coords and y coord. These are the coordinates here. In the summary, you have depth, you have pH, potential and hydrogen. These are it's about groundwater data, and we have sulfate and nitrates. So we are going to predict pH and to the depth of the well in temperature of the well. Okay, so we take the coordinates from my data. Okay, so it's brackets instead of parentheses, comma, and the C we have a vector x coord and y coord. Okay, so let's type chords. And C. So this is the two columns. We have okay. Let's now split the data set into training and testing. This is step 3. Step 1 is about libraries. Step 2 is about loading the data set. So step 3 is splitting the data set into training and testing data. We'll have we'll take 30%, 20%. Split. So take our sample IDS, IDX equal to sample from 1 to the number of rows in my data. Mm, 0.8 multiplied the number of rows in my data. Sample ID is equal to sample 1 is the column here and rows instead of no rows and row my data 0.8 divide and row my data with this and this. This is wrong. this is closed, this is closed, closed. Okay. Yep. Good. Okay, now we have train data equal to my data. For my data, we take sample IDX. And we have this data. For my data, this is brackets here minus sample IDX. Testing data sets. We also need the coordinates. Let's to run. And the coordinates, you need train coords and the test coord as well. So train coords equal coords sample IDX. Let's train coordinates and the test coords equal to coords minus sample IDX. So since you have 100 data, if you look at the dimensions, we verifying dimensions. Dim train data. So this is here. It's 80. The testing is going to be 20. And dim train coords 80. So the testing is going to be 20. Okay, now the step 4 is to search for the optimal bandwidth. We are going to use the bandwidth search function. Of the geographical random forest. So BW underscore search, let's call it that way, the object equal to geographical random forest dot bandwidth. A formula is pH, so delta depth plus T temperature. So our variable of interest pH as the dependent variable, and the independent variables are depth and temperature. And we are going to run it on the training data set. Data set equal to training data. Comma, the chords equal to train chords. The kernel, we already said it here, is fixed. Kernel equal to fix. The minimum neighbors to test, so bandwidth min, w dot min, start with 1000, set minimum neighbors test. So here is distance in our case. So bandwidth dot max equal to 20,000. This is the max neighbors test, neighbors of distance, and the step equal to go by 2000. So this is the increment of our charge, our search. So increment of the search. Okay, so let's run the bandwidth search. So it's going to take a while. We are going to continue typing. Let's print the BW search dollar. We want the best BW. Okay, and then next step is, let's say this is 4, 3 is searching for the optimal bandwidth. No, 4 is searching for the optimal bandwidth. 3 is splitting. 4 is searching for the optimal bandwidth. 5 is training our model. Training yes, model using the training data set. Okay, this already tells us here that the optimal bandwidth is 17,000. So this is what we will be using. Okay, the training. So we have our geographical weighted random forest model, or just geographical random forest equal to GRF function in the formula, the same pH filter def plus T G frame data frame equal train data bandwidth so this is a distance map unit. In this case is 17,000. So what you have is from here. So let's run this code. Okay, so you have 17,000. It's already here also. So 17,000. This is our optimal bandwidth. Excuse me. And then the kernel is fixed. And the coordinates, train coordinates, and then the entry, number of trees, and the forest true. And we want it to be weighted, specially weighted if you want to. So we will set to true, weighted true. With weighted true would work. So this is our model train. So we have the information here. This is still working. And then the step 6, question 5. Step 6 is model performance metrics. It's have training matrix and then testing matrix. We consider three matrices here: R square and RMSC and MAE. So to have the training matrix, we need to predict on the training data set. So train reds equal to, okay, it's already completed. So this is the information we have from global and local. This global machine learning model summary, the information you have with the importance, and then the local model summary with the information out of bag on R square, out of bag. Okay, now train. We're going to predict. So predict dot grf geographical random forest. The model is our DW GWRF model. We use train data. The x var x.var.name, just the x coordinates, that's equal to x coordinate in our data set. In the y dot name equal to y chord the local weights is local weight w local w equal 1, and the global w equal to 0. Okay. So error in objects forest local ID attempt to select less than 1 in until next. It is wrong here. Okay, come on. Okay, let's set this whiteboard. Let's go whiteboard. This may cause problem. Okay. Good. So now B, we need to extract the matrix, extract the actual pH values from the training data. Getting the actual from the training data set. So we have our predicted pH. We need the actual pH. So we call it train actual. Equal to train data $pH. So from train data we take our pH. Then point C is the computation of the matrix. One is returning R squared. We need train R2 equal to 1 minus sum of train actual minus train pads all squared. Excuse me. Divided by minus sign gives 1 minus sum of train actual minus train pads divided by the sum of actual train actual minus the mean of train actual. Here squared okay, so this is the formula. Run let's print it in C. Print train it's about 71% the training as well. So let's have the training root mean squared. So it's train MSE RMSE equal square root of the mean of 10 actual minus train plates. The plates squared. So parenthesis is missing here. 1, 2. The square root in the middle. Excuse me, I've added this. So print train, let me see. T is missing here. Sorry about that. And then have the training, mean absolute zero. Train MAE equal to the mean of the absolute value of the training TH minus predict. Train plates. So print okay. So these are the training metrics. Now let's have our testing metrics. To have our testing metrics, we need to make prediction on the testing dataset. But before that, we need our pH values from the testing dataset. So test actual. So let's have, okay, we can test actual. Equal to test data pH. Test data dollar pH. Okay. And now we make prediction. Let's put it in B and A, making prediction on the testing dataset. just come here for the sake of time, copy this, and just replace. Is it not that big? Okay. Okay, let's try. Okay. Let's. Just waste of time. So mistake. I should just say here we call it test point. And here we change by test, and everything is the same. And now we have this actual. We can now output the matrix. Test R square, testing R squared, it test R2 equal to 1 minus sum of actual minus test actual minus test spreads squared divided by sum of test actual minus mean of test actual. Square and up here is 2. And here one more close, and in between here we have squares here. It's wrong. It's okay. We already had it. Right here. Close here, already close. Okay, let's start. No, this is 1 here. Oh, good. Okay, we run. And we print test square, test R squared. sorry, but the title was rapid. Okay. No, there's something wrong with this. Okay, let me. So, okay. First R square equal 1 minus parentheses sum double parentheses test actual minus test spreads. Okay. Double squared. Okay. And then double parentheses divide by the sum of two parentheses here as well. Test actual minus min of test actual. Okay. Squared. Yeah. Okay. And then now we count it. Still something. Negative or square. Oh, surprising. Okay, let's try. I'm going to try. I thought I made a mistake on the formula. Let's take here and I change every train by test and let's see. Paste here. Say test R square by test actual. Here test spread. Test actual. Test actual. And we run and we count. Okay, good. So negative R square on testing data. So it means that the model is not good at us as well. So let's have the testing. Put mean square error. So the test RMC equal to square root of the mean of test actual minus test spread. Square. Let me verify something quickly on the training. test. Let me see. 0.49 almost. Okay, let's go through the training data and verify. Train MSC. Okay, here there is typo. We need 2 parentheses here. See here, we close. Okay. So 0.27. So sorry, I missed something here. So 1, 2, 3. No, 1, 2, 3. Okay, so the parentheses didn't match here. So I missed 1. 1, 2, 3. We close 1, 2, 3. Okay. So here 1, 2, 3. We close 1, 2, 3. Okay, good. So let's now go to our testing in absolute error. Test MAE equal to the mean of the absolute value in of ABS S structure minus test points. Okay, good. So let's have let's put everything together as a summary table. Let's see performance summary table. So performance summary equal to, we have here data frame. We need to comment here. Performance summary equal to data dot frame parenthesis. We have the metrics. In our matrix here, we have a vector of r squared squared. Okay, RMSC MA. So MA, and then and create another vector training C, and this time vector of train squared train MSC and train MAE. have this time testing. We grant a vector of the testing matrix. So we have test R2 test RMSC and test MAE. Okay, run, and we print it. Print performance summary F. Okay, this is what we got. So training information and testing information. We go to the matrix in the table. Okay, so next step, it's going to be 0.7. Now the visualization part. So we need to visualize. Let's call it main visualization. Plots. Diagnostic. Okay, so the first actual versus predicted plots. For this purpose, we need two libraries. ggplot 2. We install it and then we load it, and the second is Patchwell. Patch. This library is to have the two plots side by side. Excuse me. So we need a function. And the function to create the plots. We call it geographical random forest. Geographical random forest performance plot. You can name it anything you want, as long as it makes sense. So I call it geographical random forest performance plot. Excuse me, I'm having allergies. Function, we have actual, we have predicted, and then we have title. Okay. We have curly brackets. function actual predicted in parentheses curly bracket. So the curly bracket we are going to create a data frame. Def equal data frame. In the data frame we have actual equal to actual with capital A equal to actual with lower a, and then predicted equal to predicted. We have capital letters, lower letters. Okay. And then after our data frame we have the ggplots. The ggplots. In the ggplots we have our data frame. We have the AS. So we plot with the x-axis we have actual, and the y-axis is predicted. And then plus now we have the geometry point. In the geometry point we have alpha equal 0.5. We have color, take still blue. And plus geom AB line. Geom AB line we have our intercept 0, so we have the line of best fit. Intercept equal to 0, slope equal to 1. Have line type equal to dash. You can choose what you want. So dash, any type you want. Line type dash, and then color red. Okay. Yeah. Let's take the size as well. Color red, size equal 1. Okay. Then plus. Now the labels. We add the labels. Have title. Requires the title. Comma. And you need the subtitle. Equal to is no parentheses quote squared colon after the quote comma, and then we round again parentheses, and you have the formula of the root mean square error. no, they are squared. So 1 minus parenthesis sum double parenthesis here, so actual minus predicted. Okay. Square do, and then divide it by the sum of actual minus mean of actual. Okay, this 2 after 2 parentheses squared. Okay, after 2 parentheses comma, then 3, then after 3 2 parentheses comma. Okay, so we need the x-axis and y-axis. X-axis, y-axis, x equal to actual values, comma, and the y-axis will have predicted values. Okay, and then after the parentheses here we add our team minimal. Minimal parentheses. So this is the function. Okay, we are running. It's okay. So now we are going to generate plots. So A is creating function. B is generating plots. Okay. So let's have our plot 1 or figure 1 equal to the name of our function graph performance plot. We have a train actual, comma, train paths, comma, training performance in quotes. Okay, so generating plots. So here is testing plot. Train plot. Let's select the figure 1 and let's see. is here. That is method error. What's wrong? Actually not found. Okay, it's here. So this is on the training data set. So let's have a testing plot. Called fig2 equal to grf performance plot our function, and then we have a test action and test tiredness, comma, and then testing performance. And now let's merge the two plots. It's just fig1 plus fig2. Still running. Okay, so you have two side by side the two plots, the training performance and the testing performance. Okay, so hopefully in your data set, with your data set, you will get a higher testing performance, but here it's negative. So it means that we cannot use the geographical random forest to predict this, to create a model of this data. So now let's go to the spatial distribution plot with the residuals. That may be important to have an idea about the residuals of the data set, how they are distributed. So if we say this, the first plot, so let's say this one pattern, the percent pattern is to have your training testing plots side by side, which the R square, and the second plot is about spatial distribution. the noise, spatial distribution. So for this we need the residuals for the map. We need the residuals. Basically, we will have the residual maps. Okay, so in the training data set and in the testing as well. So let's have our residuals on the training data set. So let's call them training residuals. Train resid for residuals. Train resids equal train data pH minus train pred. So it's the actual pH minus predicted pH. This is the residuals of the pH. So now the plot itself. Plot, ggplot, train data, s equal so x equal to x code, camera y equal to y code, color equal to our train resids. We want to color the train resids plus 2 parentheses close, right? Plus now we have our geometry point. We have alpha. We take 25 plus geom. No, the scale color gradient 2. Scale color gradient 2, we have low. Let's take the RGB. So we go red. The mid equal to green, RGB, red, green, blue, and then high equal to blue. So low residuals are in red, mid residuals are in green, and high residuals are in blue. Basically what it means here. And then plus it's a minimal. Label title, next title, and the special distribution of training residuals. Right, let's run here. Train visit. Did you run that? Okay, train visit here. So, reduce instead of visits. Resid. Train resid. Residuals. So, that might be the mistake. Train visit plan. Okay. Okay, so this is the special distribution of training residuals. If you need to, if you are not testing, you just copy this space and you change everything train by test. So you have just 2 or 3 modification to make. So you have okay, on the testing data, here is test result. Equal to test pH, test data pH. Next test price. Okay, so I have test result we run first. Then here we have test data. Here we are going to have the test result. Okay, and here special distribution of testing. Copying and pasting is not my strength because sometimes you make mistakes somewhere and when you type it you figure out. That's exactly what happened with R squared, the RMSE formula. So we run going to have my computer is becoming slow. Okay, the special distribution of testing results. So if you want to, sometimes having residuals is required. So now another point, 0.98. So it's about special autocorrelation. We need Moran here. Here we need the library SPDEP, SPDEP, SPDEP. Okay. After having the library already, we need to have labels, a list of neighbors on which we are going to work. So make the test of creating a list of neighbors for the test. So we need first special object coordinates equal st as sf. So we need to transform the coordinates into coordinates sf. So this data course SF equal STS-SF, test data, course equal to the vector of X course and Y course. Equals of course. Okay. Run it, so now we create the neighbors, numbers, the list of neighbors. So we use K and N, 2NB function, K nearest neighbors function. So the K nearing, K near neighbor, K near neighbor. So on ST coordinates, parentheses our course SF, and K we take K equal 5. Okay. Excuse me. So okay, K will be, let's move it K near neighbor, ST coordinates course with 5, K equal 5. Okay, so running. So let's have the weight. Need the weight for the neurons I, W equal NB2 list. W NB2 list W NB labels and the style equal to upper W. Okay. So once we have our W, we can now run the Moran test. Let's call it Moran. Okay. Equal Moran dot test. Test on test result and W. And then print Moran. Okay, this is the Moran information. On the residuals, of course. And one more thing we need to deal with is the feature importance. It's also important here. If you want to extract all of the two, so both extracting the importance of both features. And call it this is local feature importance, better importance of the features for both. We call this for local EMP, local importance, we call it 2 from our model. So yes, dot data frame, that's data frame, parenthesis, we have our model, geographically weighted random forest model, dollar sign in the local variable importance. This point here, dollar local dot variable dot importance. That's data dot frame. Okay, so the parenthesis should be, yeah, parenthesis should be this here. Yes, and then local and so this is what we have. The local importance of our two variables at the same time. So if you want to extract individual importances, so we first need to convert the data frame into an SF object. So let's work on training. So train data. Sorry, I press on the okay, train data SF equal to st plus sf train data equals equal to x or plus vectors and it's called common records. I'm sorry about that. Okay, and then the coordinate reference system here, CRS 4326. STSSF underscore here underscore instead of dash. Okay, so now we need def local importance. Okay, let's from train data SF dollar def importance equal our model geographically weighted and forest model dollar local sorry dot variable importance and then dollar def. Okay, so you can't type it. Okay, this for that. You can give it an object name here, like a def importance and equal to this, and when you print def importance, you have it. We do this for the sake of plotting, so we need to map it. Mapping the local importance of def. So this we use the TM shape train data SF plus TM dots parentheses column, need the column of def importance. And then palette equal to this. You can put the title here, def importance. If you want to command the title, okay, palette double T instead of triple. Okay, so the def importance. can see here in the local data importance map, the depth local importance map. So do the same for temperature, clean data. You can just cut and paste and change everything by temperature or T. Importance equal to geographical with random forest model we created. Dollar local point variable point importance dollar T. So we come here, run, and this is the importance of temperature. And if you want to map it, TM shape and then data and save. So also TM dots column T importance. Palette equal to Eurydice. You can add the title if you want to as well. Okay, we are at the end of this video, so we have the importance here. So thank you very much for watching. I think it has been a little bit long. So yeah, this video is about when the data has normal distribution, uniformly distributed. So the next video is going to be about when the data is normally distributed in one area and dense in another area. So we'll be using adaptive bandwidth. So next is a case of dense. So we'll be, instead of using fixed, it's going to be adaptive. And yeah, I hope this video will help some people who are doing research in using geographical random forest. So the most important is to have your bandwidth, you have your metrics, and you have your plots, and the neurons as well. Yeah, and there are more things. Yeah, this I think we cover some essential points here. So Thank you for watching this video, and I see you next time for another.